Not it.
Dude, I got like a 50 or a 40 on the phone.
I got that. I think I got a 50.
Second one and third one I didn't find.
And we're doing nearly as far as.
Now, the first one is unreasonably difficult.
Yeah.
I don't understand.
I can think this is a post solution.
What?
He doesn't post a solution, so really don't know what he did wrong.
But what I learned is that he doesn't really care about the actual answer. He just solves small. Like that's what I did for all the other exams. So like
He looks just fine.
he wastes so much time trying to actually solve it. He just solves it multiply, and he'll like maybe dock you 1 point. I don't know though.
Yeah.
I never got 100 wrong. So
That's somebody. He's like. I upgrade when I see numbers. So if you put the numbers right off the bat, I go based off the last.
to be fair, it sucks trying to grade the numbers because when people get unit conversions wrong and they have to like give you partial credit, but not too much. And you get it right. They're just solid smart. Make their job.
You saw it. I think so. It's everything here. You're used to solving it sometimes. I know it's trying to practice it way. So you get like this weird combination of letters, which is the same slope.
Yeah, I genuinely didn't bother plugging it was like 40 minutes worth of problem to plug into the I'd rather just go to the next one and try and get more points.
Yeah.
But yeah, be prepared for a interesting first exam.
I'm not even looking there hard, just always tomorrow.
But the quiz is usually like litmus expert exam. Take it just really boring and figure it out, study it out. Or find somebody and prepare it before you.
Yeah.
Right, yeah, so I was like.
Still had it last week.
Oh, you actually try not. This was happening in engineering. Is it that bad? Yeah. Oh gosh, purple.
Yeah. Yeah. When something is structured, it's how it is. I'm hoping that like for us, 30 people will leave. So then a few people go in.
It's nasty.
It's not my favorite part of the advice.
That would be,
So.
yeah, that would make too much sense. But instead they made it hard instead.
But they're still going to keep selling.
They are. I'm gonna say.
Not just selling parking pass, not selling for $300.
And this one passed.
But I guess it's the line and that kind of thing, do it.
And this one passed down Boston.
They could sell it for, they could also probably sell it for $1,000. Although I think it'll be right.
It's not that bad. That's just engineering.
Yeah, no, but I'm certainly curious. You know what, I'm just saying. Or, really.
I mean, every month.
I don't really know what you're doing, but drawing on it. Yeah, I know. Wait, on homework two, one of them says off. I don't know if that means off or is that just like.
I'm thinking this and.
Make sure before I can. It's off.
I'm thinking it's John.
I'm still on that, I forgot. Companies work at this one time. Once.
But I always get it, like, meetings and this lowest thing, and I always think it was.
Yeah, you see that word.
Yesterday she pulled it out when I saw
Time to
her,
get
she
it.
just like, here, I thought you were gonna say first.
It's not much here.
It's, she stretched. it.
I guess.
Yeah.
It's like, and it's all night, but then it's quite retired.
You honestly, you guys.
I just like.
All right, it's 1 o'clock. Let's go and get started, everybody. Right after, good afternoon. How's everyone doing today? Good. Everyone have a good weekend? Anyone watch Super Bowl? Yeah, it was a good game. I had friends over at my place for the Super Bowl. Compared to last year, I actually had some friends who were invested in the results. monetarily, I mean, so some people left the party not very happy, but that's just how it is, I guess, but, okay. So the plan for today, we have just a little bit of the notes for present worth analysis to finish up. I basically just have one example to kind of illustrate to you guys what a capitalized cost is and how that's used. And then we're gonna move on to the next thing. So the next topic is called annual cash flow analysis. And you'll see it's actually quite similar to present worth. Okay. All right. So announcements, homework 2 has been posted. So make sure you guys get started on that. It's all about just cash flow conversions and present worth analysis. So make sure you start that. Compared to the first homework for this class is usually pretty short. Second homework is a lot more lengthy. So make sure you guys are getting started on that early. So the due date for that homework is going to be next Wednesday. So next Wednesday, so you have a little bit over a week to work on it. Okay. All right. Any questions I can answer before we get started for today?
Is it 11:59 AM or PM?
PM.
Okay.
Yeah. Okay. All right, let's go and get started. Okay, so last Thursday, we left off on this idea called capitalized cost. So this is kind of the conclusion of a present worth analysis, right? So, for the last few class sessions, we've been talking about this idea of using present worths to do economic comparisons, right? And what that meant was basically that whenever you have a project, whenever you have an alternative or you're budgeting for something, it's always useful to take all of the costs and all the benefits associated with it and transform it into one lump sum in the present, right? Because if you do that, then you kind of are able to do like a fair comparison of different economic alternatives to see what's best. Okay, so capitalized costs, this is kind of the last thing there. And so the idea with capitalized costs is that, for situations where you have a project with an infinite time horizon. Okay. So these are projects that are planned to basically be in service for all of eternity. Okay. So a lot of times this falls on projects that fall under this category, things like public works projects, the roads, the sewers, the traffic lights, things like that. Okay. So oftentimes, these systems here have to be maintained on a regular basis, right? And so you have to generate money, on a regular basis to maintain these projects. Oftentimes what's useful, very much in the spirit of present worth analysis, is to transform those infinite maintenance costs into one lump sum in the present. Okay. Where, kind of the context behind this is that, if you were to take this single lump sum and invest it in an account with a fixed interest rate, the idea is that you can just withdraw the dividends, or you can just withdraw the interest each year to pay for this yearly maintenance costs. Okay. And the formula for this is quite simple. So it's basically just P, where P here is our capitalized cost. This is equal to A divided by the interest rate. Okay. Where A here, this is the maintenance costs. Or whatever regular recurring costs that you need to maintain your project. Okay. I'm calling it a maintenance cost here just because that's typically what it is. But sometimes you may have other costs that go into it as well. But just basically just a yearly sum. Okay. And then I, of course, here is our interest. Okay. So the reason, we have this in its own separate category is that when you have a project with an infinite time horizon, you can't exactly plug infinity into your formulas, and our compound interest table don't have infinity on it as well, right? So we have to take a slightly different approach here for that. Okay. All right, so let's do an example to kind of show you this in action, and to see kind of how this kind of plays out. All right, so for this example, let's say that the city of LA plans to build a pipeline to transport water from a nearby reservoir. Okay. The cost of this pipeline is $8 million. And this pipeline is unique. And so the pipeline doesn't need to have regular maintenance, but it does need to be replaced every 70 years. Okay. And so if we assume a 7% interest rate, what we want to compute here is the capitalized cost for building and maintaining this pipeline. Yep. All right. It's not stated in the problem, but we're part of the assumption here is that after 70 years, the pipe is going to again cost $8 million. Okay? So what you have is a situation where you have this reoccurring cost of $8 million, but it's only going to occur once every 70 years. Okay, and so the cash flow diagram looks something like this. I'm not gonna draw 70 tick marks, but let's say that we start at year 0, then eventually get to year 70, we skip some more, 40, skip some more, to 10. Okay. All right, so every 70 years, you're gonna have a cost of $8 million. All right, so with that in mind, what the city wants to do is that the city basically wants to compute a capitalized cost. Okay, so what that means is that they want to set aside the money today to not only pay for the construction of the pipeline, but to also pay for all of its future replacements. Okay. Okay. And the assumption, of course, is that any money that they put in excess of $8 million, that's going to be invested at a yearly interest rate of 7%, and so that's going to accrue money, over that time period, and eventually pay for the replacement. Okay. Okay. All right, so basically what we have here is we have one future sum of $8 million, right? We're only going to look at the first time period because whatever we compute is going to be forwarded to the next one as well. Okay. Okay. And so we want to compute the capitalized costs for this. Okay. All right. So let's get started. So we know, well, we know one thing already. We know that today, in order to just build the pipeline, we need to spend $8 million up front. Okay. To that, okay, to that $8 million, we're going to add an investment to eventually pay for its replacement. All right, so what we have is the replacement is going to take place in 70 years. Okay. So we're going to say F is equal to $8 million. And so to compute this to put this in terms of a capitalized cost, we need to first convert this to a uniform series, right? Because even though the costs are only occurring once every 70 years, one way to look at it is, a yearly cost of X that we're going to save up until that time. Okay? All right, so to perform this conversion, we're basically going from F to A. We can use our compound interest table for this because this is a set time period, so a set time period of 70 years. Okay, so we have A is equal to 8 million. Okay, and the conversion we want is A over F. Okay, our interest rate is 7%, and our time period here is 70 years. All right, so this is something we can look up in the table. So I do have the exact decimal here. So the exact decimal for this conversion factor from the table is 0.00062. Okay. And so this A, when you multiply, is 4,960. And so what this tells us is that if the city invests just about $5,000, so if the city invests $4,960 per year into an account with a 7% interest rate, they're going to have $7 or $8 million at the end of 70 years. Okay. All right, and if that were the question, right? If that were the question in terms of how much would the city have to invest each year, that would be the answer. Okay. But this question isn't asking for that. In fact, the situation is actually a little bit different than what we've computed here already. Because not only do we need to buy a replacement at 70 years, we need to buy a replacement at 140 years, at 210 years, 280 years, 350 years, right? This is something that's being planned to last forever. Okay. And so to account for that, we need to convert this into a capitalized cost. All right, and so to do that, we're just going to use the formula that we had above. Okay, so our capitalized cost P is equal to A divided by I. Okay. Right, so pretty straightforward. So we have the A is 4,960. Our interest rate is 0.07. So we plug both those in and we get 71,000. Okay. All right. And so if the city invests $71,000 today and then let that account, grow in interest each year by 7% for 70 years, then by the end of that time, they'll have $8 million. Okay. So the total cost to build this pipeline. Okay. We have our initial $8 million. So that's the $8 million we're paying up front just to build the thing to begin with. Okay. Plus the 71,000 that's going to eventually pay for its replacement. Okay. So the total amount of cost for this example here is $8,071,000. All right. So capitalized cost problems, not too difficult. I mean, the formula is literally just, one thing divided by another thing. I think the difficulty is more kind of understanding kind of what's going on and what you need to compute and how you need to convert things. Okay. So that's why for this example, it was I think I spent more time talking than we did actually running numbers through. Just because for this example, it's most important to kind of understand what's going on and where everything's going and how to use the formulas. Okay. All right. Any questions on this example here? Okay. All right. So that does it for present worth analysis, and so that's everything you need for homework 2. So you should definitely be able to get started on that. So let's go ahead and move on. So the next topic that we're going to go over is something called annual cash flow analysis. Okay. So annual cash flow analysis, technically it's a different technique. And what we're going to learn over the next few weeks are kind of different analysis techniques. But it's very close to present worth analysis. In fact, I always call it just a very close cousin. The cousin that, maybe just 1 year apart that you grew up with, you're really close with. So you kind of end up being almost the same person. So annual cash flow analysis is very similar to present worth. In fact, it can be annual cash flow analysis can be used in all the same situations as present worth. Okay, so its goal is exactly the same. And that the goal of an annual cash flow analysis is to perform an economic comparison. Right. So for all the annual cash flow problems, you'll see that you're going to be given at least 2 options. Okay. And you want to find out which is the most viable or the most efficient economic alternative. Okay? The difference here is that with annual cash flow analysis, instead of converting everything to a present sum, you're instead going to convert everything to a uniform series, so a single uniform series. Right? That's literally the only difference. Right? And so instead of doing your conversions from something to P, you're going to convert to an A instead. Okay. Right. So fundamentally, it's exactly the same thing. It's just if you really want to boil it down, it's just that in these problems you're going to look at a different column of the compound interest table. Instead of a P to something, you're going to go to A, right? That's the only difference. Okay? So usually, for annual cash flow analysis, I don't spend too much time. We do a few examples. There's a couple new wrinkles with annual cash flow analysis. But for the most part, we're just kind of repeating the same thing. Okay. So then you may be asking, why are we going through this then? So if it's mostly the same as present worth analysis, why even have a whole nother unit dedicated to it? Well, in some situations, an annual cash flow analysis may be preferred just for the ease of understanding. So in particular, annual cash flow analysis is useful for understanding total costs, right? And so, a lot of times, when you have a project that you're kind of maintaining over, many, many years, it's useful to think about how much money you're going to spend each year to maintain that project. Mhm. Okay. Another case where they're particularly useful is in the repayment of a loan, okay? Because that's traditionally how you repay a loan, right? So you usually get one lump sum in the beginning, and you pay it off in regular installments after that. Okay. In fact, the last thing that we'll do in this unit, probably not today, but probably on Thursday, is how to build something called an amortization table. Okay, which is a very popular tool to use when you're doing like a mortgage loan or or an auto loan, something like that. Okay, to plan the payments. Okay. Um, Yeah, so the situations, a lot of times present worth analysis and annual cash flow analysis, you can interchange the two. It's just that in certain contexts, just to make things a little bit easier to understand, annual cash flow analysis may be a little bit easier to understand, but by and large, you're going to go through the same process. Okay. Okay. So before we jump into an example, there is a little bit of a little bit of terminology that we need to go through. Okay. So I have three terms for you here. So the first one is called equivalent uniform annual cost. You'll see me abbreviate that as EUAC often, just because it's more convenient. Okay. So the equivalent uniform annual cost. This is all the costs associated with the current project converted to a uniform series. Next, we have equivalent uniform annual benefit. And that also has an acronym, EUAB, okay? Right, so this one, probably hopefully straightforward. So instead of all the costs, these are all the benefits associated with the project. So these are all positive cash flows that you're taking in, converted to a uniform series. Okay. All right, and the third one is just a combination of the first two. Is called equivalent uniform annual worth. Okay. And that also is shortened to EUAW. And all this is just EUAB subtracted from EUAC. Okay. So EUAW. So it's all the costs and all the benefits associated with the project converted into one uniform series. Okay. You take EUAB minus EUAC. Okay. Or more commonly, I think what you'll see is that you're just going to take all the cash flows for a given project or a given alternative and convert that directly to a uniform series. Okay. So I bring these up, these terms are, they make a lot of sense when you read them. It's just that it takes a long time to say equivalent uniform annual worth. So you'll hear me just say EUAW. And that's all it means. It's just converting all the cash flows to a uniform series. Okay. All right. Any questions on this before we jump into an example? Okay. All right. Let's do an example. So this example here is a repeat. So we did this example with present worth analysis. We're just going to redo the example using annual cash flow analysis. Okay, so let me summarize what that example says. And so in this example, you're working for an engineering company that needs to purchase a machine to support its operations. Okay, and there are two options it's considering. All right, so we have machine A. Machine A has an initial cost of $10,000. Okay. And due to the capacity of the machine, from the product that the machine produces or the workflow that it saves, you can consider the machine to produce $3,000 a year in revenue. Okay, and then we have machine B. So machine B has an initial cost of 13,500. Okay. The revenue that it produces is also $3,000 per year. But machine B also has this gradient effect. And so it's going to earn you $3,000 in the first year, but this is going to ramp up by $500 each year. So machine B has a little bit of a larger initial cost, but you have this ramp up period. Okay. Okay. And so the number of time periods for both machines is going to be 5. Okay. And our interest rate here is 7%. All right, and so your company wants to find out which machine should it buy. Should it invest in machine A or should it invest in machine B? Okay, so we did this analysis last time with present worth analysis. So in present worth analysis, we took all the cash flows for machine A, converted that into a present sum. We took all the cash flows for machine B, convert that to a present sum, and we saw whichever one was higher or most positive. Okay. So we're going to do the same thing, but with annual cash flow analysis. And so we're going to compute the equivalent uniform annual worth of each machine and just see whichever one's higher. Okay, so let's start with machine A. All right, so what we want to compute is the EUAW, or the equivalent uniform annual worth of machine A. Okay. And so to do that, we need to convert all of its cash flows into a uniform series. Okay. Okay. So machine A here has 2 cash flows. So we have its initial cost of $10,000. Okay, so we're going to put a minus 10,000. We need to convert this into a uniform series, right? So that $10,000 is an initial cost, so that means it is a present sum. So that means we want to do an A over P conversion, okay? Converting from a present sum to a uniform series. Our interest rate that we have is 7%, and our number of time periods is 5. Okay. And then to this, we're going to add the revenue. And the revenue is already given to us in uniform series format because it's given to us as $3,000 per year. So that's already a uniform series. So we can just add 3,000 to this. Okay. And so we can look up this conversion factor in the compound interest tables. And so if we look this up, this A over P factor, this is 0.2439. Okay. And so we just perform the arithmetic. We have a minus 10,000 times 0.2439 plus 3,000. Okay. We add that up. And what we get from that is 561. Okay. All right. So what that means is that if the company invests in machine A, right, even though initially they're going to have to pay $10,000, okay, but the net effect over that 5-year period of investing in machine A means that the company earns $561 per year, okay, on average. Okay, so let's do the same for machine B. Okay. So you have EUAW, B. Okay. We're to convert all of its cash flows into a uniform series. All right, so first we have the initial cost. So our initial cost is 13,500. A over P, 7%, and then 5. Okay. We have our $3,000 per year revenue. Okay, so that's plus 3,000. And then we have our ramp effect, right? And so we have our gradient of 500. We need to convert this to a uniform series. And so this is going to be an A over G. Okay. Converting from a gradient to a uniform series. Interest rate is 7%. And the number of time periods is 5. Okay. Okay. So once again, we're going to look up these conversion factors in the table. This A over P factor is the same as above. So this is going to be 0.2439. That second conversion factor is new, and so we need to look that up in the table. And so this conversion factor is 1.865. Okay, and so we plug those in, we get our final answer for the EUAW machine B. And it's $640. All right. So now that we computed the EUAW of both of those options, and so we're just going to see which one is more positive or higher, and we can see that machine B is the higher option. Okay? And so based on this analysis here, the company should purchase machine B.
So what's the difference in terms of steps that you're doing here in comparison to what was it, present sum conversion?
Yeah. So the main difference is in the conversion factor that we're looking at. And so you know, you can see here that our in the numerator there is an A instead of a P, right? So we're converting everything to a uniform series here. And also, you have to look at the problem here and see, which cash flow type that number is in already, right? So if you look back on our previous example, we didn't apply any conversion factor to the 10,000 because that 10,000 was already in a present sum, and so there was no need to convert it. Where we actually applied the conversion was on the 3,000 because that 3,000 was a uniform series, and we needed to convert that to a present sum. So this time it's the opposite. So since we're converting to a uniform series, we actually apply the conversion onto the initial cost, but we don't apply it onto the revenue, right? So it all depends on kind of what you're converting to and what form the given cash flow is in to start with. All right, any other questions on this example here? Okay. All right, so yeah, but other than that, largely the same steps. It's just just applying different conversion factors. Okay, let's throw a wrinkle into this. Well, it's not really a wrinkle. It's actually a nice thing. All right, so if you recall, after we introduced the idea of present worth analysis, we talked about the importance of the time period. Okay? And so in present worth analysis, in order to perform a fair comparison, the length or the n value for each of the alternatives must be the same. Okay? If they weren't, right? If you were considering two alternatives with a different time period, right? So let's say one lasted, 4 years, the other lasted 8 years. We had to extend our analysis to the least common multiple. Okay? So in those situations where you have different alternatives with different project lives, it presented kind of an additional complication. And at the end of the day, it just kind of ended up just being a little bit annoying more than anything. Okay. If you do annual cash flow analysis, and so if you convert everything to a uniform series, you actually don't have to worry about this. So it's kind of a nice benefit of doing this. Okay. And in fact, this is one of the primary reasons why people use annual cash flow, where if you're comparing, different options with different product lives, it's just more convenient to use annual cash flow because you don't have to extend the analysis, you don't have to buy replacements, you don't have to find the least common multiple. It's just kind of one less step for you to do. Okay. And the reason you don't have to do this for annual cash flow is that it's a uniform series is naturally a recurring type of cash flow. Right? You're not summing up together, the product of 7-8 years of stuff into one lump sum. The fact that it's kind of naturally distributed means that it's you don't have to account for different product lumps. Okay. All right. So to show this, let's do an analysis, or let's do a fairly lengthy example where we kind of do it both ways. And so we'll do an example where we buy the replacement and we compute its EUAW. Okay. And then we'll do the same example where we don't buy the replacement. And then, you'll see that we get the exact same answer. Okay. So in this example here, let's say that we are planning on purchasing a new pump. Okay. All right. So I believe this was an example we did last time as well. Okay. Okay. So we have pump A, pump B. Okay. So both pumps, they have an initial cost. We're also given the salvage value of both pumps. So in both cases, when the pump reaches its end of life, we can sell its parts for some money. Okay. And then each pump has its own useful life as well, just how long the pump is rated to last. Okay, so the initial cost for pump A, $7,000. Okay. Salvage value for pump A is $1,200. And pump A is slated to last for 12 years. Sorry. 12,000 years would be a long time. It'd be the best pump in the world. All right. Pump B, we have our initial cost of $5,000. Okay, so it's a little bit cheaper. Okay. The salvage value for pump B is going to be 1,000. But pump B is only slated to last for 6 years. Okay. Before we have to replace it. Okay. And so what we want to do is we want to use annual cash flow analysis to determine which of these pumps we should buy. Okay. Oh, we need the interest rate. I always forget to do that. Okay, so we have an interest rate of 7%. Okay. So we have a situation here with different product lines. Okay. Normally, if we were to do this with annual cash flow analysis, what we would have to do for pump B is we would have to extend its life. Okay? Okay. And we would extend its life to the least common multiple between the two options, which in this case is 12 years, right? And so we would buy a pump B, we'd buy one pump B at year 0, okay? And then to make it last until the end of 12 years, we'd buy a replacement at year 6, okay? And then, once we did that, then we could compute its present worth. Okay. What we'll see is that when you're doing annual cash flow analysis, you don't need to do that at all. Okay, so let's do the analysis straight up first, and then I'll show you the analysis when we buy the replacement. Okay, so let's compute the EUAW of each pump. Okay, so let's compute the EUAW of pump A. Okay. So this is first we have our initial cost. So our initial cost is $7,000. So we have a minus 7,000. A over P. %7% and 12. Okay, so we're distributing, one way to look at that is that we're distributing that $7,000 across 12 years. Okay, taking interest rates into account. That's why we have this cash flow conversion. Okay. And then we have our salvage value. So our salvage value is $1,200. Okay. That $1,200 is something that we realize at the end of the project life. Okay. And so this is a future sum that's occurring in year 12. And to convert that into a uniform series, we need an A over F conversion factor. Okay. Interest rate of 7% and time period of 12, just like before. Okay. All right, so just like we normally do, we can look these up in the table. Okay. Our handy dandy compound interest table. And so this first conversion factor here is 0.1259. Okay. And the second conversion factor here is 0.0559. Okay. All right, and so we punch all those numbers in and we get EUAW of pump A to B. Minus $814,000. Minus $814. Sorry about that. Not $814. That'd be crazy. Okay. All right. So what this is telling us is that when you take that initial cost and you kind of spread it out over the first over the 12 years, okay, taking interest rates into account, it would be about the same as $814. Okay. Okay, so let's do the same thing for pump B. Okay. But I'm not going to extend this. And so I'm just going to take this straight up using the 6 years. Okay. So this is no replacement. Okay, so we're just going to convert everything that's associated with pump D to a uniform series, but only using the 6 years. Okay, so this is going to be a minus 5,000 for the initial cost. A over P, 7%. Instead of 12 years, we're converting this over 6 years. Then we have a salvage value of $1,000. That is a future sum. And so we're going to convert that to a uniform series. So that's A over F, 7% and 6. Okay, so let's look these up in the table. Okay. Keep in mind that we're doing this for 6 years now. And so that's going to be a different row in the table compared to 12. And so this right here is going to be 0.2098. Okay. And then this A over F factor here for 6 years is 0.1398. All right, and so we punch those into a calculator, and what we get is minus $909. Okay, so based on this analysis here, we can see the one that is less negative is pump A. Okay, and so in this case, we should go with pump A. Because that's the one that's going to minimize the cost. Okay. Any questions on how we did that so far? All right, but wait a minute, right? And so this analysis was done just kind of completely ignoring the product lines, right? And so we just took the product life straight up. We said pump A lasts for 12 years. We plugged in 12 for our conversion. We said pump B lasts for 6 years, so we plugged in 6 years into our conversion. Okay. You know, when you have different numbers here, you know, it seems like, you know, this is not complete, right? Because we learned a lot during the present worth analysis that the time period makes a big impact on the results. Okay. So let's see. So let's redo the EUAW for pump B, but let's buy a replacement in year 6 so that we can get up to the 12th year. Okay. And so our cash flow diagram looks like the following. Okay, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so we're basically extending our analysis from pump B until the 12 years. Okay. And so initially for this one, we have our initial cost of $5,000. Okay. And then in year 6, we're going to salvage that pump for 1,000. Okay. All right. But then in year 6, in order to get us to the end of year 12, we need to buy a replacement. So we're going to buy a replacement pump here. Okay. Again, we're going to assume that our replacement pump has the same cost as before, so it's going to cost $5,000. Okay. And then at the end of year 12, we're going to have a $1,000. Okay. So that would be salvaging the second pump. All right. So let's take this cash flow diagram and convert it to a uniform series, you know, and compare it to what we had before. Okay. All right. We have to be a little bit careful with this though, and so because this conversion here is not as straightforward as it seems, because this falls into the category of a non-standard cash flow conversion. Okay. Okay. And it has to do with the replacement. Okay? Because remember, you know, when we talked about standard forms for each of these cash flows, when you're converting something from, you know, say a present sum to a uniform series, you know, the assumption is that the end stays the same. Okay? And so if we were to take this lump sum in year 6 and convert it straight to a uniform series, okay, right? So what we would use in that case would be an n of 6 because it occurs in year 6 of our timeline here, right? The uniform series that you would compute would only be from years 1 through 6. But we don't want that in this case. We actually want a uniform series that stretches over the entire 12-year span. Okay. And so to do that, we need to do multiple conversions here. Spread out. Okay. So to spread this this lump sum over 12 years, we have to do 2 cash flow conversions. Okay. All right, so let's focus on that one first. Okay, so what we have here is a single lump sum in year 6 that we want to distribute as a uniform series across all 12 years. So in year 6, okay, we have 2 different cash flows that are occurring in year 6, but because they're happening at the same time, we can kind of just lump them together, right? And so we have a salvage value of 1,000 that's coming from our first pump, and then the purchase of the second pump, the initial cost of 5,000, right? So we have a total of 1,000 minus 5,000, which is minus $4,000. Okay. All right, so we have a minus 4,000, and right now this is occurring in year 6. Okay. Okay, so there's a few ways to go about this. And so, the way that I usually like to do is I first like to convert everything to a present sum. Okay. So to convert this to a present sum, we need a P over F. P over F, 7% 6. And so what this is going to do, this whole unit right here is gonna take our minus 4,000 and convert it to the present day. So that's the first step. Okay. Because once you have a lump sum in the present day, you can do almost anything you want from that, because there are conversion factors that go from P to something else for every type of cash flow. Okay. Okay, because what we want to do from here is we want to distribute this or convert it to a uniform series across 12 years. So this is going to be A over P, 7%, and 12. Okay. And so what this one right here does is that it converts present sum so that present sum that we converted in the blue, we're gonna now spread that out over the 12 years in the pink. Okay. And so we're going to look up these conversion factors. So this P over F one right here, this is going to be 0.6663. Okay. And then our A over P conversion here is 0.1259. Okay. So we multiply these together, and what we get is minus 335 and 55 cents. Okay. So I wanted to highlight that cash flow conversion because it is a non-standard one, right? And then on the homework set that I just posted today, or yesterday, there's a whole problem with non-standard conversion. So there's three problems like this, right? The non-standard conversions at first, I think when you first see them, they can be really confusing. And so it really helps to kind of see examples like this and kind of talk through the logic, so that you kind of start to get the hang. Any questions on how we did that non-standard conversion there? Okay. All right, but we're not done just yet, because this cash flow diagram has more than just that non-standard conversion. We have our initial cost as well as our final salvage value. Okay. But luckily these are much easier to convert, just because they happen at the very beginning, at the very end. Okay. Okay, so let's incorporate that initial cost and final salvage. And so we have our EUAW of pump B. Okay. We have the non-standard one that we just converted. So this is the minus 335.55. Okay. So that's the non-standard one that occurs in year 6 that we just did. Okay. Next, we have our initial cost. So our initial cost is $5,000. So we have a minus 5,000. A over P, 7%, and 12. And then we have our final salvage value of $1,000. Okay, so that's a positive 1,000. A over F, 7% and 12. Okay. All right, so we add all these together, and what we get is minus $909. Okay. All right, so that's the EUAW that we get if we do buy a replacement, right? So remember, we did, this whole shebang that we just did here was kind of in the same fashion that we did present worth analysis. Okay, so we bought a replacement and then we incorporated that into our analysis. Okay, let's look at this number and let's compare the EUAW that we got without doing this whole replacement business. Okay. Let's scroll back up a little bit. So what I have here is the EUAW that we computed for pump B, but without buying the replacement. And so we just did it for the 6 years that it's rated for. Okay. So we took the $5,000, converted to a uniform series with an N value of 6, and we took our salvage value, we converted to a uniform series with an N value of 6. So no replacement at all, just one lifetime. Okay. And what we got from this was an EUAW of $909 minus 909. And then if we buy the replacement and we incorporate it, we get the exact same thing. Okay. And so this illustrates that if you're doing annual cash flow analysis, you don't have to worry about the time period. You don't have to worry about them matching up between the different alternatives. Okay. All right. Any questions on this? I always love it when you do an example like this and it kind of, it ends up being kind of the same thing, right? So, but I also understand the perspective of like, we spent 20 minutes, doing this example, buying the replacement, and we end up with the same fucking thing that we had before. So, and so you can see, we just wasted 20 minutes, but it's the same. So it kind of shows you that it's you don't have to do this in the future. Okay. So that's nice, right? And so when you're doing economic comparisons, and you have different product lives, annual cash flow is usually the better option because it just ends up being a little bit less complicated for you to do. Okay. That's not to say that you can't do present worth analysis. You certainly still can do present worth. It's just that you still just have to incorporate that. Okay. But both methods are equally viable. They're going to give you the same result. Okay. It's just that annual cash flow kind of saves you. It saves you a little bit of work. It saves you a step. Okay. But there is a caveat to this. Okay? And so you can do this. You can use annual cash flow without worrying about a replacement if you assume that you are going to buy a replacement in this situation. Okay? And so for something like a pump, right? And of course, all of this is very context dependent. It depends on kind of what industry that you're working with, what your project actually is. Okay. So for an example like a pump, I think the exact context that we gave for it last time was that it was just for the power company, right? So that seems like something that the power company plans to use for a very long period of time. And so even when a pump reaches its end of life, you can assume that the company's going to buy a replacement for it and keep it in operation. Okay. So in those situations, if you're planning on buying a replacement anyway, eventually, then you can do this. You can essentially ignore the product life and do annual cash flow analysis. Okay. If you have a situation where your project life is finite, okay, and so you're only planning to buy one of these or two of these, and then you're going to move on to something else. Present worth analysis with buying a replacement might be a better option for that. Okay. Okay. And so all this is very context dependent. Okay. And so it depends on your industry and things like that. For the purpose of this class, I'll tell you in the problem whether you can make this assumption or not, but it's something to keep in mind, if you're going to apply this technique outside of this class. Okay. Okay. Any questions on this? Okay. All right, so a couple more definitions in the last 5 minutes, and then we'll wrap it up for today. Okay. 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 So the first term, and these are kind of more trivia than anything. Okay. So one term that you may come across is this term called a capital recovery cost. Okay. Um, and what this refers to are situations that happen quite often in engineering. So what this refers to is that whenever you have to buy a large capital expenditure, right? So you have to do a very large upfront cost. So this is quite common for situations when you're buying a large piece of equipment or maybe a vehicle or machine. Okay? Very common things in engineering. Um, the the capital recovery cost is the equivalent uniform annual cost for these capital investments. Because usually, when you buy a large piece of equipment like this, companies are often interested in terms of, how quickly can we recover this cost, right? So we bought this machine for $10,000, and with the promise that this machine is going to generate some revenue or generate some cost savings for us. Okay. So how long is that going to take? And at what yearly rate is it going to take to recover that capital? Okay. All right. Any questions on this? Okay. All right. So the next thing is kind of a new topic. I don't really want to start in the last 2 minutes, so we'll wrap it up a little bit early today. But when we come back on Thursday, we'll finish up these lecture notes. There's not really much to it. So this is annual cash flow analysis in a nutshell. So we're going to spend most of the next class talking about loans and how to analyze those within the context of annual cash flow. All right. So thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you on Thursday.
Yeah, I have them for.